Okay, today we will discuss Chapter 7, Deadlocks in Operating System. This is the last part of Chapter 7. If you guys remember, we discussed the deadlock prevention strategies. We discussed the violation, how we can violate the conditions of deadlock. Today we will talk about deadlock detection and avoidance scheme, how we can detect or how we can avoid a deadlock. Mostly for avoidance of the deadlock, we use Banker's algorithm, and for the Banker's algorithm, it's basically for with Banker algorithm we can detect the deadlock. We can also avoid the deadlock. So in Banker's algorithm, we need to give detailed information. We need to give detailed information to operating system about all incoming processes. For example, what kind of information? For example, let's say which processes are coming, We need to tell operating system like how much resources are required. Then we need to tell the holding time as well, like for how long they're gonna hold the resources, etc., etc. And then operating system can make decision whether whether that process can be entertained or not on the basis of all this information. In Banker's algorithm, what exactly we do? In Banker's algorithm, the operating system makes a safe sequence. So safe sequence is basically a safe sequence of the resources, like in which sequence I have to allocate the resources to different processes. So safe sequence means there will be no deadlock. And for example, if Banker algorithm cannot make a safe sequence, then it means deadlock will occur. So let's understand Banker's algorithm with a small example. So let's say we have three resources. For example, I have three resources, R1, R2, and R3. So I have, for example, 10 resources of R1, for example, 5 resources of R2, and 7 resources of R3. R1 could be, let's say, it could be a CPU. Let's say it could be a CPU. For example, I have 10 CPU maybe. R2 could be a memory. For example, I have 5 main memory chunks maybe. R3 could be, for example, printer. I might have 7 printers, something like that. So let's say I have 3 main resources, R1, R2, R5, and I have 10 instances of R1, 5 instances of R2, and 7 instances of R3. And let's say I have 5 processes, P1, P2, P3, P4, and P5. Let's say I have 5 processes which will share these resources, or which are gonna use these resources. This is basically the allocation table. If you can see this table, let me explain you table, and then I'll design a safe sequence by using that table. So if you see, I have enlisted processes right here. Allocation mean these are basically currently resources have been allocated to these processes. Like process 1 has one instant of R2. It has not been assigned R1, R2, R3. It is currently using 2 resources or 2 instances of R1, no R2, R3, and same is the case with other processes. Maximum need means like process 1 needs 7 resources of R1, 5 instances of R2, 3 instances of R3. If you assign these resources, process 1 can execute successfully and it can terminate itself. Same is the case with others. Like P2 required 3 R1, 2 R2, 2 R3. Same is the case with others. And this is, by the way, allocated. We have already allocated that. Now, firstly, let's see how currently how many resources are available. So if you see, in order to see how much currently resources are available, we need to actually count all these allocated resources. How many resources are allocated? So if you see R1, 2, 3, and 7. So 7 R1 has been allocated. R2, 1, 2. So 2 R2 has been allocated. R3, 2, 3, and 5. So 7 to 5. So 7 instances of R2, R1 has been allocated. 2 instances of R2 have been allocated, and 5 instances of R3 have been allocated. So currently, how many resources are available? We need to actually, if you see, 10 R1 were available, 10 R1, 5, 7. These were the total resources which were available. We need to subtract allocated minus the total. So if you subtract 7 to 5 from here, 7 to 5, if we subtract it, so we have 3 instances of R2 currently, R1 available, 3 instances of R2, and 2 instances of R3 available. Now currently we have 3 R1 available, 3 R2, and 2 R1, 2 R3 instances are available. Now remaining need is, we next week calculate the remaining need. What is the remaining need of all processes beside the beside the allocated? So if you see, we in order to do that, we need to subtract allocated minus maximum. So allocated R1, we have not allocated any R1, so it requires all these 7 resources. It requires remaining, it requires all 7. 1 instance of R2 has been allocated, so maximum is 5. 5 minus 1 is 4. 0, 3. 3 minus 0 is 3. It means we need all the 3 resources for process 1. For process 2, 2 instances of R1 has been allocated. Maximum is 3, and 2 has been allocated. So 1, and then we need we have not assigned any R2, R3, so we need 2 R2, 2 R3. For R3, 3 have been allocated, 9 are required, 6. We need more 6 resources. We don't need any kind of resource. R2 required, R2 0. 2 R3 instances have been allocated, and 3 were required or maximum, so 0 required. So subtract this 2, 1, and 1. And then we have for P5, we need, if you subtract that, so we need 5. Minus this, we need 3, and then 1. So these are the remaining resources required to all these 5 processes. And this is our currently availability. So firstly, we'll see, can we accommodate, can we entertain the process P1? Can we allocate based on the current available resource? So if you see, it requires 7 R1, and we just have 3 R1. It requires 4 instances of R2, we have 3. So it requires R3, 3 R3, we have 2. So it means we are out of resources. We cannot accommodate, or we cannot actually execute P1. So what we will do in Banker algorithm, we'll actually see the process P2. Process P2 require 1 instance of R1, we have 3. 2 R2, we have 3. 2, we have 2. So it means we can actually successfully execute process P2. So process P2 can be executed because its remaining need remaining need falls well within our current availability. So what will happen? Firstly, the sequence is going to be, we will execute P2. So we will allocate all these current resources to P2 and get it done. Once P2 will be executed, it will release the currently held resources. So held resources will be, released, and these resources, once we allocate that, automatically it will release the resources. So once it will release the held resources, so current resources will be increased, like these 2 instances of R1 will be back. Now if we add these held resources to R1, it's gonna be 5. There were no, so 5, 3, 2. So these 2 resources will go back here. 3 plus 2 will be, is 5. Once P2 will be executed. Now P2 is executed, it is terminated. We are done with P2. So P2 is executed, it is terminated. Next, we will check our process P3. Again, it requires 6 instances of R1. We just have 5. although it doesn't require R2 and R3, but we cannot satisfy because it requires 6 and we have 5 only. So we will go to next. Next is P4. It requires 2 instances of R1, 1 instance of R2, 1 instance of R3. So it means we can 100% satisfy that. So next, see in the same sequence, next process will be P4. And now P4 can be executed. Of course, we will allocate the resources. It will be allocated, and after it will be terminated, it will release the held resources. These are the held resources 2, 1, 1. So we will add 2, 1, 1 will be back. So now 5 plus 2 is 7, 4, 3. Now we have 7 plus 7, 4, 3 resources, and we have executed P1, P2, and P4. Next we will check P5. So of course we can execute P5, absolutely right, we can do that. If we see 5 are required, we have 7. It requires 3 R2 instances, we have 4, 1, we got plenty of, so we can execute that. So next is in our sequence is going to be P5. Now P5 will be here. Once P5 will be executed, it will release the held resources. Held resources are 0, 0, 2. So now 7, 4, 5. Now if you go back here, so now we will go back to our, because it's kind of we cannot pick the specific one. We will actually go back to the first iteration. So the first is 7, 4, 3. If you see 7, 4, 3 P1, so we have 7 R1, we can do that. 4 we can do that. We can entertain R3 as well. So next in the sequence is going to be P1. Okay, so once P1 will be executed, it will release its resources. So now 0, 1, 0. Now we have 7, 5, 5. These are the resources. So now last process is P5. Now we can entertain P5 as well. It requires 6. We have 7. So we will get P3. So we will now execute P3. Once P3 will be executed, it will release the held resources. The held is 3. These are held resources 3, 0, 2. Once we add it, 10, 5, 7. So after all the processes are executed and terminated, you can see over all the resources, operating system have reclaimed all the resources, which were 10, 5, 7. 10, 5, 7. So this is the safe sequence that operating system will follow by using this banking algorithms, where we have detailed information about all the processes and everything. So by using this sequence, deadlock will not occur. Please remember, if at any stage, if operating system fails to make a safe sequence like this, it means it is unsafe. And once it is unsafe, it means there is a possibility of deadlock. Okay, and of course there will be no safe sequence. If you cannot make such sequence, it means deadlock will definitely occur. So this is the banker's algorithm. So please, you can actually follow. There is. I'm gonna actually upload the assignment for banker algorithm, a lab 3 in fact. So please let me know if you guys need any help.